one thing is, uh, we always want that more and more people, more and more students, they should come towards fundamental science. What C.V. Raman sir has done with a very small instrument, that's a much bigger inspiration we should draw from that. And trying to invite more and more students to become scientists, go to fundamental research, because we have seen during lockdown, also during Corona, that basic science research that matters a lot. Because if everybody will become engineer or a doctor, perhaps they will apply the science or whatever research, but we always need to update. So we want more and more people to be scientists, but how to become a scientist? That is sometime a question. So for that, we have specially requested, and we have with us Professor Mayank N Vahia, who is a retired professor from Tata Institute of Fundamental Research, having a long exposure, a friend of Science Center, not only Nehru Science Center, but the entire Council of National Council of Science Museum. He is our planning and programming committee member and chairman as well. Served in various society, means various positions so far as our Nehru Science Center committees are concerned. He was also chairman or the national coordinator for Astronomy Olympiad program for more than a decade, if I remember it correctly, or even more. Yeah. Uh, Now he has served with, I think, as dean of mathematical school in NMIS, and now he's a freelancer. But it's always a treat to listen to him. I'm also personally a big fan. Some of you, I will just share one line, and then I think we'll have some couple of minutes. In Astronomy Olympiad program, which I had opportunity to coordinate several times, means arranging at Nehru Science Center, and for a long since 1999, I was involved in that. And Professor Vaya's one lecture, which is always a talked means talk of the town, I should say, which runs from for almost 8 hours continuously, right from scratch of physics up to the modern physics or space, covering in his lecture for a order of 10 to the power minus 16 to 10 to the power 25, and similarly the entire physics. Those who have listened, perhaps I know all of you have, must not have got that opportunity, but today is an opportunity to listen to him. He is a great science communicator, great orator. So be very careful and attentive in your whatever you have. I don't know if sir allows, you can ask question in between, but otherwise you can note down at the end. We'll try to take up some of the questions, whatever is possible. Because I remember in one of the lecture he said, "Let us have question answer session. Who stops first? Whether he stops giving answer first or you stops asking question." So all those things we have witnessed. It's a great opportunity to have Professor Vaya with us on this very special day, National Science Day. I'll request him, sir, to come on the dais, and I'll request Ms. Danya Samani from JV Parekh to welcome Professor Vaya on behalf of all of us by presenting a potted plant. Welcome, sir. And now I think I can hand over the mic and stage to Professor Vaya to start talk and then start the lecture. So over to you.
Good morning, all of you. I think we are not telling that. YouTube. Okay, so then I can't start till 10:30. Yeah. Okay. Now can you hear me? Ah, now you can hear. Um, First of all, it's a pleasure and privilege to be here. And I'm grateful to Nehru Science Center for giving me this opportunity to talk to you. And of course, thank you very much for coming. It would have been so. It's a great pleasure talking to you. Um, so, what I'm going to talk about, I mean, we'll of course talk about the great C.V. Raman and his work initially, and then we will go on to talk about how one becomes a scientist. What it is does it take to become a scientist? And that's what we will do. Can I have a slide changer? Yeah. So we are going to talk about C.V. Raman and what he did and why do we celebrate 28th of February and what happened on 28th of February that makes it the National Science Day. And why do we choose, of course, C.V. Raman's work? There are so many great names of that time. Uh, the two Boses, the Satyendranath Bose and SN. The two Bose, Bhabha, Sarabhai, a whole bunch of people were there at that time. So why do we single out C.V. Raman? One obvious answer is that he got Nobel Prize for his work, and Nobel Prize is the highest prize for of recognition for any scientist. And C.V. Raman is the only Indian who worked in India and got that award. There are Indians who have settled in other countries who have got, but C.V. Raman did his entire work in India. So C.V. Raman was an interesting person. He was right from the beginning committed to science and thinking about science and working on that. But the question was that what did he do? And the uniqueness of his work is very remarkable. So C.V. Raman, just to give you the basic data, he was born in 1888 and he passed away on November 1970. So you can do your subtraction, almost 90 years. He is known for his work on scattering of light. And it sounds somewhat trivial, and scattering of light basically is essentially happening to all of you. The light from the ceiling is falling on you. You and your clothes are scattering it. Some of that scattering light comes to me, and therefore I can see you. So it seems very, very sort of benign kind of a thing as to why scattering of light should be so important as to get a Nobel Prize. But the interesting thing is that I'll come to a little later. He worked with one of his students called K.S. Krishnan. Now, K.S. Krishnan himself is a very renowned, he would go on to do some great things in science. We all know about the double helix research, which got Nobel Prize for DNA. He also discovered, before the double helix was discovered, in fact, he had discovered another molecule which was triple helix. And that also remains a landmark piece of work in science, but he didn't actually formally get the Nobel Prize. The Nobel Prize for scattering of light was given to C.V. Raman on his own, but K.S. Krishnan was also a remarkable scientist of his own right. And they studied how light is deflected. So his question was straightforward. His question was that we know the sky is blue because shorter wavelength light is scattered much more than the longer wavelength light. So if you have dust particles in the sky, the longer wavelength will simply ride through and the shorter wavelengths will get reflected. And that is how all the sunlight that comes, the red radiation essentially passes through and the blue radiation gets scattered, and that is why the sky looks blue. That was known since 1860s or so. But the question that C.V. Raman had, and the story has it that while he was traveling the Mediterranean, while everybody was looking at the sceneries, he was worried about the color of water. Water, after all, is not a mirror. So it is not that the sunlight falling on the water gets reflected like a mirror, and therefore it is a blue color. His question was, why is the sea blue. It's a different shade of blue. It's not the same shade of blue as the sky. So obviously the surface of water is not a mirror. And that water is doing something to the light that falls on it. And that is why the water of light, or the color of water was slightly different. So his entire obsession while traveling through Mediterranean was to worry about why is the water color blue. It is not a mirror system. What is going on? Why is the water color blue? And in fact, he pursued that study for several decades. He made special instruments to do that and all that. And eventually he realized that there is something profoundly important that happens to light when it passes through a transparent medium. And his entire Nobel Prize winning work was on this idea as to what happens when light passes through something transparent. And he got his Nobel Prize in 1930. And the reason why we celebrate National Science Day today is because it was on February 28, 1926, I think, that he first announced this result of his study to the world. And that is why we celebrate that. The day the Raman effect was announced to the world was 28th February. That is why we celebrate National Science Day. He got Nobel Prize for it 3-4 years later for that outstanding piece of work. He was incidentally the first Asian to receive the Nobel Prize in any branch of science, in fact. He's also done a lot of work on Indian musical instruments, but I won't talk about it because I want to talk about something else. So he started with the money that he got from Nobel Prize. Incidentally, he started the Raman Research Institute, which is there in Bangalore, which is doing some extraordinary work in science today. So Raman effect, what is Raman effect? Raman effect is a very peculiar thing. Like I said, it worries about how light passes through a medium. So the first behavior is simply like a billiard ball. The light falls on the atom and then it gets reflected by it without any changes. And that is elastic scattering. Nothing special happens to the light remains unchanged, the water molecule remains unchanged, and nothing happens. But as for a small fraction of photons, a small fraction of light, it actually goes and interacts with the atom on which it is falling. And when it falls on that atom, strange things happen. So you have the light that is coming straight in. Either it can bounce off like it bounces on from a ball, and then nothing special happens. And this has been known. It's called Rayleigh scattering. It had been known for 50 years, even when Raman began his work. But Raman found two more effects. He says when this light interacts with the atom, not just bounces off the atom, then strange things happen. Either its energy can decrease or its energy can increase. If the energy decreases, it is called Raman scattering. And if the energy increases, it is called the second form of Raman scattering, Raman-Stokes effect. So what happens is that you have this molecule of here, light is coming in, light gets sort of entangled with the with the atom, and when it releases back, something strange happens. Some of its energy is either lost to the atom, or atom, if it was coming in the right direction, will actually enhance its energy content. So you can have both kind of. You have change in frequency and wavelength of light when it interacts with it. It happens only in 1 part in 10,000. So if you put 10,000 light photons on the material, 9,999 will simply bounce off as if it is a football. But 1 part in 10,000 or so will actually be affected by Raman scattering. Essentially what happens is that if you take this as the energy band of an atom, so the nucleus is at the bottom, and the closest the electron can be is over here. Typically, if you vibrate an atom, you get infrared light. What Rayleigh said was that if an light falls on that atom, it goes, the energy is increased, it comes back to the same level, and you get your photon back, and nothing interesting happens. What Stokes-Raman effect said was that sometimes what happens is that this light is reflected to a higher level, but then comes back to a lower level. And the result is that the outcoming energy of the photon is less. Or it can be reversed. It can go to high and then come back go from a higher level and come back, in which case it is higher energy. And this is called the Raman effect. And as you can imagine, it is specific to the molecule because these energy levels that you get are specific to an atom or a molecule. So while Rayleigh scattering is standard, it happens the same way against all the elements. So a Raman effect is very sensitive to which molecule you are talking about. So the Raman scattering in water will be different from Raman scattering in alcohol and so on. So Raman studied this effect in great detail. He built his own spectrograph to do that, and he built it in uh, great detail. And Raman effect was announced, like I said, in 28, sorry, 2 years before he got the Nobel Prize. The effect is used by scientists in a variety of purposes. Many other variants of spectroscopy are now allow us to study how molecules are structured and how they behave. Electron level of atoms, etc. You can use it all the way for X-rays to understand even atoms individually. So this is what happens. Rayleigh scattering is when an atom is hit by a light photon, it gets a little excited, but releases the photon back without anything significant. Raman effect on its own says that, look, it may get excited, but because of the nature of atom, it may get scattered differently. And this difference in energy between the incident light and outcoming light will tell you about the structure of the atom or the molecule that you're talking about. If there is an exact energy level fits, then this in fact becomes very efficient. It very efficiently absorbs that wavelength light and re-emits it another wavelength. And this will again tell you about the structure. And occasionally, if you have one of those radon watches which has fluorescence, now they are not there. Once upon a time, they were in great fashion. But their fluorescence, this is what happens. When the light falls on it, that light energy gets stored in that atom and it gives you an afterglow a little later. And you can see the energy in difference when you measure the energy of the photon. So the one that is directly reflected will show up like this. Its energy won't change. But there are photons whose energy changes because of the nature of the atom on which it is hitting. And therefore, this is called Rayleigh and Rayleigh-Stokes scattering. And that is a very useful technology to have. Because I can make light incident on all kinds of things. I can do endoscopy. I can put a light detector and a light source in my stomach, light up the light, and the light detector will see, largely it will see Rayleigh scattering, but it will also see Raman scattering. And when it sees Raman scattering, it will tell you what kind of molecules exist in your stomach. You can do it for individual tissues, you can do it for malignant tissues, you can do it for doing when the molecules are, cells are splitting and so on, and a whole bunch of effects for which you can now use this Raman effect, because Raman tells you exactly what kind of molecule is there and how it is behaving sorry, in that medium. So why did Raman succeed? What is it that Raman did that other did not? Raman succeeded because he thought very deeply about what was going on. Why was it going on? Coming from Mediterranean, where he first realized the question, all the way to coming back in India for several decades and working on that, he persisted with that problem for several years, asking himself as to why this light in water looks different. And he was not satisfied until he understood what was going on. And his understanding produced work which in many ways changed a lot of things we do. He saw that the blue seas emerging light, like I said, is different from the blue light that is falling on it. And that question alone would take him to a Nobel Prize. He was convinced that there was more to scattering of light than simple reflection. And he set up experiments, he had his own spectrograph and all that. So he built instruments from scratch just to understand why the blue water looks different from the blue sky. So the question is, what is science and what is scientific research? And that's what I'm going to think. Science essentially is a study of the working of nature. How does nature do the things that it does. Okay. The idea that you have is if something is happening to nature, if you have an idea about how something is happening, go back and ask nature whether it is really happening that way. So Raman had a feeling that when the light falls on a transparent medium, maybe the molecules of water change the nature of that light. So he had that idea. He made an instrument and he checked it against experiments to confirm that his ideas were correct. Science, therefore, not only predicts, but it explains why this is done. So it is different from other knowledge systems where people just predict. If you go to an astrologer, he'll simply tell you that whatever, you will get fortune in some time or the other, etc. There is no explaining as to why. I mean, effect of planets, etc. Planets are so far away, it is trivial to show that the effects don't work. So they simply predict without any rationale. Science does both, predicts and explains. Science is also objective. There is nobody of authority in science. Nature is the only way, nature is the only arbiter, nature is the only one who checks whether your ideas are correct or wrong. The only way you check your ideas, whether they are right or wrong, is by doing experiments. And anyone can study science. It does not require any special skills or special ability. It's only a question of desire to be a scientist. So scientist, like I said, is a systematic study of the working of nature. It is a study that is beautiful and elegant because nature herself is beautiful and elegant. The way plants work, the way everything happens around is so beautiful that you cannot help but realize how beautiful and elegant it is. Scientists, therefore, what they do is ask questions to nature about why something is happening the way it is happening. And then nature will give you back an answer. So in case of Raman, he asked nature as to why water looks different in blue than the sky. And nature said, look, this is what it looks like. Now you go and figure it out. And then he said, wait a minute, is something special happening? So nature said, maybe, but it is for you to find out. So he set up these experiments, and sure enough, nature told him that something different happens. So you get an answer from nature, and you check your answer with increasing precision in order to arrive at the exact answer. And so every time you ask a question to nature, so Raman on the boat asked the question as to why blue in the river seas is different from blue in the sky. So nature said that is how it is. He went back and asked whether it is because of molecules. And nature said, yes, it is because of molecules. But what about molecules? And he went on going deeper and deeper into the question until it becomes an infinite loop. And I'll give you an example about how science becomes an infinite loop of questions. That is all you do. You ask question, get an answer, frame your question better, and ask again. Okay. Nature is the final arbiter in telling you why something is happening. There is no person with final authority. There is no authority who says this is how it is done. It is just nature. And the nice thing about nature's, your ideas as far as working of nature is concerned, is that they are falsifiable. You can prove them to be false. And I'll show you examples where scientific ideas people have thought of, which look very attractive, but nature said, no, that is not how I work. And those ideas are failed. So that happens. Falsifiability is an important part of the story. You can prove something is true or false. And that is how it differs from other fields of human learning. So scientist essentially is a lifelong student. You do only study, except that your teacher now is not a specific teacher, but nature is your teacher. You keep on talking to nature, you keep on asking questions to nature, you keep on asking how things happen the way they do. A scientist, therefore, is a student, but who believes only in what nature tells him. There is no, like I said, authoritative person who can tell. Some people may help you get an answer, but eventually the answer has to be found by yourself. Nature can be quite confusing in its answers. And I'll come to an example of that. But nature is not required to be straightforward, and nature is not. So understanding the answer is not always easy, and I will show you examples of how answers themselves are complicated. So scientists takes no authority other than nature, like I said, and history of science is full of ideas that looked very attractive, but nature didn't behave that way, so we just gave up on those. The believe that by chemistry you can change elements. So there were people who worked on trying to convert lead into gold and so on. Obviously, those experiments didn't work because that is not how nature works. So these ideas got thrown away. But alchemy is a major field where people try to convert lead into gold. Also, it was believed first initially that all the planets go around the Earth. Now we know that is not the case. When you really tested that theory, it turns out that the planets go around the sun and not around the Earth. But there were several centuries for which people believed this to be the truth. Then there are people, there was an idea at some time that people can see something because my eyes emit light which is reflected back. We now know that that is not true. Similarly, it was believed that there was a universal fluid or gas that filled up the entire universe, which was called ether, and into which everything is immersed. And now we know that that is not true. The universe is vacuum. Similarly, there are people who believe that the earth was flat. We know that is not true. There are people who believe that different life forms are spontaneously created. We know that is not true. Darwin showed us exactly how creation works. Astrology, of course, is another piece of nonsense. Some fields like Newtonian mechanics also were good only for some particular region of experience and not a universal theory. So these things keep happening. Science is not always unlimited, precise truth. Like we think, scientists also think. They make mistakes, they get wrong ideas, and then they check against nature and correct it as needed. So what is the purpose of research? The purpose of research is the activity of a curious mind that is curious about how nature works. The only difference between other field of learning is, like I said, science predicts and explains. Science is open tested by experimental tests. Science is falsifiable. You can prove that your idea is wrong. And science is objective. It does not believe on wisdom of anybody. It simply goes by what nature tells. And scientists, therefore, are respected because they create both science and technology. So if you look at the stamps of India, the largest number of stamps are for scientists because scientists are a fairly respectable community. And I could talk about each of these, but I shall not. So who can be a scientist? Okay. And anyone can be a good scientist if you follow the process of good science. What it needs is commitment and dedication. There is no part-time scientist. You can have a part-time engineer, you can have a part-time doctor, you can have a mediocre doctor, you can have a mediocre engineer, but you can't have a mediocre scientist. If you're a mediocre scientist, you're essentially a technician, and then the life is not much fun. What requires scientific pursuit is this commitment and dedication. Environment, if you have it, it is good, but otherwise you can build your own environment. And it requires hard work. It requires really hard work. Let us not hide that fact. Essentially, what happens is like C.V. Raman on that boat, you essentially think of why anything is happening around you all the time without having a fixed time of office or something. That obsession is what makes you a scientist. You can be, like I said, a mediocre doctor or engineer. If you're a mediocre doctor, a few people will die earlier than they should. And if you're a mediocre engineer, some building might collapse or something. But you can't be a mediocre scientist. Mediocre scientists then become technicians, and it is not much fun. So, what is the life of a scientist? The life of a scientist is the one of asking questions to nature through experiments and theory. You can ask questions on paper by writing equations and solving them. You can ask questions to nature by doing experiments. Some engineers also try to change the behavior of nature, and that is called engineering. So, for example, this room is cool because some people figured out that you can force nature to have cool gases at some places at the cost of hot gas somewhere else. And that is how we have air conditioning, which is a technology that essentially comes from science. Okay. If you ask complex question which is too complicated, you won't understand the answer. And if the question is too simple, it will give you no new information. So the entire skill of a scientist lies in selecting the questions they ask. Skill lies, therefore, in asking good questions. So what happens in other field is that science does not conform. So if you're in a research field, and if you're doing the same thing for 5 years, you're doing something wrong. The field, because every time you ask question to nature, nature has given you back an answer, and obviously you are now asking a more precise question based on the answer that you got. So obviously the field keeps changing. In all other fields, you are essentially doing similar things all the time. Over here, you are not. Okay. If you join the rat race of making lots of money, you are essentially doing a repetitive high tension activity, which gives you money, but it is essentially repetitive. Science is not. A company that pays you an amount of salary obviously expects to make 10x amount of money based on your work. In research, that is not true because you never know when you will get the answer, which is convertible to engineering. So the world of science is full of passion because you want to know how nature works. It is uncertainty because you never know what question answer nature will give. It's one of hope that you got the correct answer. It is one of progress. It is one of mistakes and learning. It is one of failures. Failures are very common in science, but persisting in the after failure is what makes a good scientist. There are, of course, successes along the way, and there's a huge amount of satisfaction to what you've done. Compared to that, if you are in other fields, you are dictated by someone else. You are in a risk-free environment largely. You are doing what is repetitive, what is predictable, and life is relatively easygoing. That is why you need all kinds of entertainments and stuff. And it is completely lacking in creativity. At the end of the day, those jobs are boring. They are easy, but they are boring, even if they give you a lot of money. So where are the questions? The questions are everywhere. So for example, I'm wearing a gray colored shirt and I can ask the question as to where is my shirt gray? And you will see how questions evolve. First of all, the first thing you realize that gray is not even a color in the spectrum. So what is going on? What is this color gray? If you're in class 5 and if your teacher asks you, why is my shirt gray? You will say it was dyed with a gray color dye, and that is how it became gray. If you're in 12th standard, you will say that your shirt reflects a current proportion of light photons from various wavelengths in the wavelength of 380 to 750 millimeters and nanometer, so that I register it as gray color. If you're in BSc, you have to show that it is coated with a pigment where the molecular structure is such that you get the right proportion of reflection of light, which gives you gray colored shirt. If you're in MSc physics, the same question as to why my shirt is gray now becomes a question about the quantum structure of the reflected photon and the energy levels of the shirt pigment which I have coated my shirt, and how the energy is deposited on the retina of my eye. If you're in BSc doing biology, the same question says the light reflected by falling on the eye's retina triggers a particular reaction in my eyes, which sends up a signal to my brain, which then registers at a gray color. And if you're doing PhD on why my shirt is gray, you have to first realize that you live in the neighborhood of a star which emits immense radiations in this wavelength. So there's a lot of light in that wavelength. Then you realize that the structure of the pigment of the shirt is such that it reflects a particular set of wavelength in relative intensity so that I can suggest it as gray. Then you have to worry about retina of your eye and how the reflected light is registered, and how when I was in school, my teacher showed me gray color and said, this is gray color. So there is a calibration that went into that when I was in the school. So a whole bunch of phenomena go up to tell me why is my shirt gray. And then you have to worry about the nerve centers in the brain, which react to various, after all, eyes are connected to the brain. It is the brain that really sees, and that reflection of response of various nerves in the brain will give you a correct set of signals, which are then compared with the calibration that your school teacher did for you to decide that the color is gray. And then you notice that because the eyes are complicated, the nerves are complicated, the brain is complicated, no two people see the same color the same way. Our responses vary. So just taking the question of why my shirt is gray becomes increasingly complex as your own understanding improves. The more you understand, the more questions you have, and that is how it takes you where it is. And the last part, when you do that, you immediately realize that gray does not even have a unique spelling. GRAY and GREY are both valid spellings for gray. The color gray, in fact, is white that is inefficiently reflected, but with a similar color spectrum. The color gray may be possible combination, and there are shades of gray. All this is gray color. And you realize how different the gray colors are. And you can have warm gray and cool gray and so on, depending on the real of yellow to blue. You realize that colors are recognized not in themselves, but in contrast with the environment. And what is called white, if the background, and sometimes you would mistake, for example, this color for white very easily if the background is not conducive. And everybody perceives colors differently, and many pigments produce the same effect. The same question you start with as to why my shirt is gray becomes increasingly more complicated and increasingly more questions. So you ask your nature, why is my shirt gray? Nature says because your pigment reflected gray color. Then you ask what is gray color? It tells you the wavelengths in which the light is reflected. Then you say, but how do I perceive it? So you say my eyes reflected. Then you say, how do my eyes see it? And then you realize that it is my brain that's seeing it. My eyes are not even seeing, they're simply transmitting the information. And then you come out with a whole bunch of realization. Your question and your answer, the dialogue with nature, looks like this. Some questions can produce increasingly interesting answers and improve your own understanding. A good question is the one that leads to good insight. And the only reason why you need teachers for PhD is because you need a training in asking good questions. But for example, in Bombay University, you can do PhD without a guide, because if you're good at asking questions, you can do it on your own. A good scientist is the one who asks good questions. Okay. So for example, what are the questions that are interesting? When you ride a bicycle on a hard road, it is easier than by riding a bicycle on a sand. And you can ask yourself why that happens. When you're reflecting sunlight, the sun itself is white and yellow, and we are told that the moon reflects the sunlight. If the sunlight is yellow, why is the moon white? There's something going on there. You can ask that there are 4 fundamental forces that work in classical mechanics, but how do I walk on the floor? Which of the 4 forces work? You can ask yourself as to why the original clocks were made with pendulums, but my wristwatch no longer has a pendulum. So what happened? You can ask yourself even more complicated question, that electromagnetic radiation and gravitational force both go as 1 by r square. I mean, one is Q1, Q2 by r square, the other is GM, M1, M2 by r square. Then why is the effect of that force so different? Why are gravitational? So you have this mass in gravity, gmm by r square, and you have mass in Newton's laws of motion. And you use the same value of mass. And there is no obvious reason why it should be the same. but it turns out to be the same, and we don't know why. Then you can ask about atomic origin of what is latent is, what is Young's modulus in the background of atomic structure of material. There are questions everywhere. The questions you can ask till the end of time, as it were. And if you keep on persisting with questions and answering questions and finding new questions and looking at the answer, you are on the road of becoming a good scientist. So how do you become scientist? First of all, ask questions, but remember that nature likes to talk in mathematics. She doesn't like very verbose discussions about what is going on. Mathematics is the root, is a language of science. But mathematics is a language of its own right. And mathematics is so full of ideas and structures and beauty that it is an independent language. It so happens that nature also likes mathematics. Nature speaks in mathematics. Good science quantifies. It does not tell you that, look, the light is reflected in correct quantity. You want to know how much of yellow light is there and how much of blue light is there, because without that, just to go back to the previous slides, if it did not quantify, you would not realize the difference between warm gray and cool gray, because only when you quantify, you realize that warm gray has 6% yellow color, while cool gray has more blue color. So you need to quantify, you need to measure. Okay. Then you need people to train you on how to ask questions and how to listen to the answer that nature gives you. Listening to nature's answer is where the fun lies. High level of mathematical complexity and adoption of mathematical tools is essentially a part of the story of studying nature. There are intuitive guesses that you can make, but they must be verified. Like I told you, so many ideas that seem to be intuitively correct, but turned out to be false. Comparison of and exploration of idea of what is known is essential. Simulations, these days people simulate a lot. Tell nature this is the situation, these are the forces that are working, how will things happen? So simulations are used very often. Other insights such as simplifying in a manner that is explainable are another way in which people do it. And then design instrumentation or instruments to make your understanding better. Whole bunch of things can be done. Okay, we need learned researchers who can ask these questions to nature and look at her answers. Why mathematics? I'll give you a simple example of why science is obsessed with mathematics. This is a pendulum. Okay. And imagine I have made a pendulum clock which ticks every second. Now I want my friend in Delhi to make a similar pendulum watch. What do I tell him? Do I tell him the length of the wire? Do I tell him whether I use cotton string or zinc string? Do I tell them that the blob was circular or square, or do I tell them whether I hung it from the ceiling or whether I hung it from my tabletop? What did I do to get me my 1 second long? Just by saying that it oscillates tells me nothing. Okay, but if I define it in mathematics, if I define it in mathematics, then it says this is the governing equation. Forget about what it means for the time being. Okay, this is the language of mathematics, which says that this is a pendulum. It's a mathematics translation of the word that this is a pendulum. What it tells you that the only thing that matters is the length of the string. You can use silk thread, you can use rubber thread, you can use cotton thread, you can use whatever you want, or metal thread, or whatever you want. You can make the blob square or circular or any arbitrary shape that you want. As long as the length is correct, you will get a pendulum of the same type. That is all that matters. The word oscillates never tells you that, but this mathematical translation tells you that, and all I need is this kind of motion in my device to make a watch. So in my watch, there is a crystal that also oscillates similarly. And that is how I can make a wristwatch, and I don't have to worry about, if I simply said it oscillates, I have to spend the rest of my life holding my hand like this because the pendulum is to swing. But now I can compact it, because once I translate it into mathematics, I know that anything that vibrates is good enough, and that is how I can make wristwatches. Mathematics gives you that power. Okay. It allows us to generalize phenomena and it allows us to advance in science. That is why you need mathematics as a tool of science. And nature loves to speak like that. What is this? Nature will tell you is simply something that obeys the law called d square x by dt square is proportional to minus kx. And that is where the power of mathematics comes. Since they both obey the equation, like I said, I can make a crystal of vibrate or I can take a pendulum, but they both give me a nice watch. So how do you become a researcher? The first rule is you can never be a part-time researcher. There is no such thing as a part-time scientist. If you want to go for science, you have to put your heart and soul into it. Okay? It's an all-encompassing passion. It is something that you have to give a heart and soul to. Like C.V. Raman enjoying a cruise on the Mediterranean was more worried about the color of the sky blue. He didn't understand the color of the water. That kind of obsession to make sure that you can understand everything that is going around you is what makes a good scientist. It is a full-time occupation. There is no such thing as a 9 to 5 scientist. To look where everyone has looked and to see where what nobody has seen is what makes science great. For example, we all know projectile motion. If I throw a piece of chalk up, it goes and falls down. Only Newton realized that the moon's movement around the earth is also a projectile motion, except that it is so far that that moon misses the horizon and therefore keeps going around. It is exactly the projectile motion, except that the length of the projectile is greater than the radius of the earth, and therefore the moon keeps going round and round. The fun, it is a kind of madness. There is no doubt that it is a kind of obsession and madness. But it is the fun in being mad that only the people who do it will realize and appreciate. And it's a wonderful exercise. Okay. Compared with other science, scientific research is about understanding and not about memorizing. Life, so coming first in SSC board or coming first in your school, etc., those are all 100-meter dash. Over the next few months, you must learn up everything so well that you pass your exam. Essentially, it's a question of memorizing well. Science and research are not a game of memorizing, but a game of understanding. There is a difference between information and knowledge. There are two different words in English language for obvious reasons. Understanding is knowledge, memorizing is information. And information brain doesn't like to store raw information. It likes to convert that into knowledge. You have to understand what you have learned. No one is a born genius. Never ever have we had born geniuses. No scientist was a born genius. Everybody like you and me started by going to school, studying the school, but passionately pursuing as to why nature is behaving the way it does. It is 99% perspiration and only 1% inspiration. And that inspiration also will not come without 99% perspiration. So make no mistake. The second thing is never worry about somebody who is better than you at any given time. Life in science is not a 100-meter dash. It's a marathon. So you have to systematically keep on going at it. For inspiration, like I said, also comes to a preparedness. All geniuses worked hard and long. And it's surprising that very few SSC top rankers actually become good scientists because they've run this life of a 100-meter dash. Please the teacher, please the examiners of 10th standard, get your maximum marks and live happily ever after. It doesn't work. It just does not work. Hard work is different from donkey work. Those who come with SSC top ranking, etc., are essentially donkey work. They've mugged up all the textbooks by heart just long enough to be able to vomit it. 6 months after the exam, if you give them the same paper, they will fail. Because they have only had information, they've never had knowledge. On the other hand, if you have taken time to understand what is going on, then on long term, that knowledge will stay with you. On short term, it may not get you the marks it does. Many schools, for example, teachers insist that you should reproduce things exactly as they taught them, etc. That is all knowledge. That is all information. That is not knowledge. Hard work is a mix of working at that syllabus and working on your own or thinking on your own. to understand what is going on. Research career is a marathon. All examinations are a 100-meter dash. In next exam, you should vomit out whatever your teacher asks you, and that is that. So there's a big difference between science and engineering, science and school performance. Who can be a scientist? There's an impression that a scientist is supposed to be foggy-minded, skinny, unfed, long-haired fellow, and that is not really true. We have a large fraction of Indian scientists or women scientists in general are women scientists and engineers, of course. Some of them are extroverts. They like to talk to lots of people, make lots of friends. Some of them are introverts who like to sit in a corner and think for themselves. Some are methodical, systematically going to do or pursue something. Some are a little less organized. They're always worried about a whole bunch of different questions, and therefore they are less organized. Some like to do it by experiments. Some like to do it on a piece of paper by theory. Some work in very specific areas and some work in very broad interests. So there is no predefining science or your liking in science or science concepts. Thinking has no preferred language. It doesn't even need that you should be fluent in English. You should learn to think. That is the bottom line. What is required is discipline and commitment. Okay. How do you achieve this? You initially need to train your mind to develop this habit. It doesn't come naturally. Okay. Then once you have done that, you simply follow it with complete dedication. And how do you study science? The first thing to do is to think science, for God's sake. Think about why everything around you works the way it does or happens around you the way it does. Second is understand the mathematics that goes behind it. Einstein, for example, one of the greatest scientists of all time, was originally considered a dud. He was in 13th at a class of 10, 8, 9, 10th. In fact, he was considered a particularly poor student. But he had an uncle who was a mathematician. So he passionately taught young Einstein a lot of mathematics, and therefore he learned the language of mathematics. So anytime he heard a physics problem, he translated it into mathematics. And when he realized about problems about ether, he wrote down the physics in mathematics, and that was enough to get him a lifelong reputation as one of the greatest scientists of all times. So you don't have to be early bright. You have to solve problems. In order to really understand the complexity, you have to quantify things. To quantify things, you have to solve problems. You have to have a historical perspective. You must realize that people try various things and fail and learn, and a whole human race, the story of human race actually is not very different from the story of a young child trying to understand how the world works. Understand language. Why are there so many different, why is there, for knowledge, why is there two different words of information and knowledge? Understand those, and you will realize how nature works. Read different books. Every author who writes a book writes it from his or her own perspective of the understanding of subject, and therefore they will never coincide with what you have. So the more books you read, you'll get different explanations from different people, and that is how you will understand things better. Respect your teachers. Teachers definitely have more knowledge than you do, and they have worked hard to convey that information to you. So just because a teacher cannot explain a particular topic very well, that doesn't mean the teacher now has to be condemned. Listen patiently to what your teachers say and build on it. Go and ask questions. Go and trouble the teacher until he or she answers your question. If he or she can't answer your question, ask somebody else. Concentrate. There is no way of doing science where you are watching a movie or something. There is no way. You have to be focused. And don't work too hard. It's surprising people who work too hard never give their mind a way of working. It's a very simple thing. Our brain has two sides, left brain and right brain. Most of our body is controlled by left brain. And that is the one that has information, that has language, that has control, motor control and everything. So whenever you ask yourself a question, it goes to the left brain. But very often you must have found an experience where you just could not solve a problem until the answer suddenly flashed in front of you. It's called the eureka moment. And that is because of our right brain. It is our right brain that works in a manner which we don't fully understand. It definitely does not use language, but it creates a structure in your mind which gives you the framework of whatever you are thinking about. And therefore, right brain needs time, it needs quiet, it needs ability to understand what is going on. That is why we sleep, for example. It is the right brain that matters. And if you keep working too hard and keep your left brain agitated, your right brain doesn't get time to understand. So give yourself time to understand and be original. No copycat ever succeeded. Think on your work, on your work. Doesn't matter if your friend thinks differently, you have to be original. And every time somebody tells you why you are wrong, listen. That person may not be right, that person may be right, but it's always good to listen to when people say that you may be wrong. And ask questions, ask lots of questions. Figure out how things are happening, either on your own or ask somebody. Science itself is changing from when I was a student to what is today. Today, our understanding of nature has improved. Therefore, our questions are also becoming more sophisticated. If you like to study now, so studying nature in isolation now has more or less been sorted out. Now people worry about the complexity of situation, where, for example, chemistry involves physics and biology and so on, and it has also become interdisciplinary. We need researchers who can ask good questions and innovate in experiments. And we also, unfortunately, also need some amount of management, because now much of the science research has gone into large groups. Okay. So simplified, isolated approach is now reaching its limit. So we need to understand simple things. So for example, asking how a system gets heated, you need to understand, to have physicists who tells you the property, a chemist who understands the chemical reactions within the material that is being heated. You need an environmental scientist to what it takes from the air and gas around you. You need an experimental apparatus and somebody to run it. You need someone to control the environment and the experiment, and you'd someone to simulate exactly what happened to get you a complete picture of what is happening to some substance when it is heated. So does that mean individuals don't matter? That is not true. Individuals still matter, because human creativity cannot be replicated. We require people to design questions that are answerable, that are not answered before, and that are interesting. You don't want somebody to ask very stupid question or trivial question. Questions that are important, questions that provide new perspective. And this can be only done by a creative mind, and that is the human mind. So changing face of research has now become multidimensional. I'm going to skip this slide because I want to go to the next one. Okay, as artificial intelligence comes in, you have a lot of assistance to help you structure things, but imagination and creativity is something only humans can do. So what are the future sense? The future virtual augmented reality, multiple sources, geoinformation, geotechnologies, remote sensing, whole bunch of fields where we require serious studies and serious scientists. Often I can list 18 different questions where we desperately need people to help us understand what is happening. There are plenty of subjects, plenty of fields, plenty of curiosities, plenty of things we do not know. So even if you're scientists or scientists that tell you that we know everything, frankly, there are so many subjects in which we don't know anywhere near what would be nice to know. So there are 20 questions. Then there are pitfalls of research. One thing is that remember that scientific knowledge has been systematically accumulated for 400 years. And therefore we know fairly large amount. Those who become, you youngsters of today will become scientists by the year 2030 or even later. And you will read the research well into the middle of the century and probably to the end of the century. Okay. And India needs to be scientifically self-aware. We need to understand how the world of science has achieved what it has, and build upon that. There was a time when India was, in fact, the epicenter of scientific research. So it is not a European enterprise at all. So we should not approach modern science as if it was something that Americans do and we have to follow. It is not. Okay. Modern India also has remarkable progress in science and technology. Science, like I said, has been a 400 years systematic study of nature. To understand that takes time. Okay. Asking questions and newly defined questions requires even more years of training. Okay. A large number of research institutions are now available in India to work on research in science and technology. So, like Indian Institute of Technology, several institutes of scientific research have come up. India now has 5 institutions called Indian Institute of Science Education, Research and Training. 40 years ago, we needed engineers. So, Indian Institute of Technologies came up. Now, the country realizes that we also need scientists. So, there are at least 5 ICERs, and there is one NICER, which essentially takes students from 12th standard and bring them up to be scientists. Then there is a Center for Basic Sciences right in Mumbai. So there are 6 such centers. Plus, IITs also have good training in pure sciences. The government has given handsome scholarship for many of these institutes. It is interesting that joining them helps, but it is not critical. If you don't get into any of these institutions, that is not the end of the line. At the end of the day, like I said, it's a marathon, and therefore wherever you are, if you remain committed, you will succeed. It is a commitment that counts. So after 12th standard, you do BSc, MSc, and PhD, which is a standard route. You can do BTech and PhD. You can do integrated BSc, MSc in some institutions and do PhD. You can do BSc and then integrated MSc, PhD. It takes about 9 to 10 years after class 12 to be fully conversant with the dynamics of working of nature or science. You should be in touch with Olympiad programs. It's a good program. Look up Olympiad program on the website. Then there are also Young Scientist Awards being given by institutions. There are journals like Resonance. There are public lectures. There are activities like what Nehru Science Center does. There are professional organizations like Homeoba Center for Science Education, Nehru Science, NCS, National Council of Science Museums, and the science centers that they have, planetariums, and so on. Plus, there are organizations like Indian Association of Physics Teachers, which organizes lectures for students. Indian Physics Association, local astronomy groups are quite common. Local science organizations are quite common. So these will give you sort of under exposure to science, which is beyond just the classroom, in order to help you understand the working of nature better. Towards the end of your studies, you can either join National Initiative on Undergraduate Science, visiting student research program, which many institutions have, or go abroad for your master's study. After you complete your studies, you can apply for PhD, you can go abroad for PhD, you can apply for research fellowships, and the bottom line is that you need to find yourself a good teacher who will show you how to ask good questions. There are plenty of research institutions in India. We are now have research institutions practically in every field of human scientific activity that you can think of. India has research institutions like devoted to everything. There is also, for example, a research institute for leather research and stuff. There are 150 institutions providing opportunity to pursue various fields of science, and many of them are in fact much better than the foreign institutions that you get. Finding jobs, there are plenty of jobs available, university and teaching jobs, there are research institutions and labs, there are industry jobs. The salaries are competitive. You'll never be a rich scientist. But then if you want to be rich, don't come to science. If you want to have a satisfactory life, then only come to science. And salaries are definitely comfortable. You also command a respect. Swadesha pujyate raja vidwan sarvatra pujyate. The king is worshipped only in his kingdom. A learned man is worshipped everywhere. There is no shortage of vacancies, but there is a shortage of good scientists. If institutions, many of the institutions today don't have enough number of scientists, not because there are no vacancies, but because they can't find good scientists. There is more, and there'll be more of that in future. The problems of the career are that there are no part-time scientists, there is no average scientist, and excellence is a minimum requirement. However, being a trained at scientific makes it easier to handle a whole bunch of other careers. Like I tell mathematics, you can go from mathematics to any other field of learning, but you can't come from any other field of learning to mathematics because of the very nature of it. So if you're trained well, very many other fields also will be very profitable with scientific way of thinking. Thank you very much. If you have any questions, you can ask. If you have any questions, yes. That boy, no. Correct. Hmm. Yeah, no. So what happens is that if Marconi and Tesla, if Marconi had not been a good scientist, his copying of Tesla would have made no sense to him. So he had to have so there are plenty of claims of copycat, but the one who is receiving the idea himself has to be a very mature scientist to be able to copy something. Okay. So for example, I can tell you all my research that I'm doing, but you won't be able to publish it because you won't be able to make much sense of it. So unless you are also at the same level of complexity. So even those who have been accused of copying others themselves are fairly competent before they went out of copy. Okay. Yes. I can't hear you. Shout. Yes.
Good morning, sir. Sir, you told that a C.V. Raman has a research on nature. Then how he find the equation? By asking the nature?
Yes. So, for example, the famous experiment of Newton. Newton took a ball and made it hit another ball. And then he measured how it goes in other direction. And he measured the velocity of that. Then he created a table and he said the best way of putting this data is to use this equation. So for example, Newton came out with this gravity because he had Kepler's laws before him. What Kepler had done is measured the parameter of all the movement of planets, created the table, and then seen which is the mathematical equation that fits the table well. So he came up with these three laws, and Newton saw that these three laws together can be done better if you just write one equation of gravity. Okay, it's a classical example of experimental data, then formulating the formula, and then putting theory into it to realize the whole picture. Okay. Yes.
Good morning, sir. So my question is, why didn't the K.S. Krishnan got the award for Nobel Prize? Because he also did a great invention.
So no, Krishnan. The general feeling is that Krishnan did triple helix, while this double helix turned out to be more important than triple helix in life. So the work of double helix turned out to be more useful than. But apart from Nobel Prize, Krishnan himself was a very highly recognized and regarded scientist of his own right.
And so one more question, that it is said that the Pythagoras theorem was founded earlier in Vedic maths. So is it true? Because
no. Yeah, I'm glad you asked that question. So what happens in India is that people try to make right angle triangle. And there are some very good some triplets, 2 square plus 3 square is 5 square and so on. In ancient Indian mathematics, people knew of the Newtonian, not Einstein, Euclid, the triplets, the Pythagoras theorem, they knew the Pythagorean triplets, that they knew that 2 plus 3, 2 square plus 3 square is 5 square and the other triplets. The reason why Pythagoras gets a recognition is because he proved that for any three sides, any right angle triangle, a square plus b square is equal to c square. That proof doesn't exist. So they knew Pythagoras theorem partially. They knew Pythagorean triplets, but not the theorem. The theorem was proved by Pythagoras. Welcome. Yes.
Sir.
Sir. One minute. Huh? So aerospace engineering requires study and engineering of rocketry and aircrafts. And there are some very good institutions, Indian Institute of Science, Bangalore, IIT, I think Bombay also has a department of aerospace engineering. Aerospace will always expand. Aircrafts will expand. Outside the Earth, travel will expand. So it's a good field, but it's an engineering field. It's not a science field. Okay. Somebody else? Yes.
Sir.
Yes.
Sir, here.
I can't see you. Will you raise your hand? I can't make out where you are. Yes, yes.
Sir, I want to talk about astronomy. So,
Yes.
what is the difference between astrophysics, astrobiology, and astrochemistry?
Okay. So, first of all, there is a difference between astronomy and space sciences. Space sciences is technology. Put rockets into space, put satellites into space and make them work, etc. In astronomy, essentially is working of nature. But nature has clouds, nature has chemicals, nature has material. So the study of physics of stars, etc., is called astrophysics. Study of the chemistry of what happens inside this cloud, the chemical reactions, etc., that happen in cloud is astrochemistry. And large molecules, large organic molecules that happen to arise in clouds eventually give you biological phenomena.
Sir, I have actually 3 questions more. What is the unique feature of the astrophysics which is not in other features of
No,
astronomy?
at this stage, the fields overlap. The astrophysicists will become astrochemists part-time and stuff like that.
Okay. Actually, I want to get in ISRO as an astrophysics. So, what qualifications and exams?
MSc Physics first.
Okay, sir.
MSc Physics and with maths background.
And
But the other students waiting to ask questions. Yes. So I gave you the example of the gray shirt. Okay, that is one example. The second example, I mean, it's difficult to give general examples because how nature answers your question. So, for example, there's a famous experiment. People said, okay, the world is filled with ether. So, if world is filled with ether, Earth is moving around in ether. So, if I throw a light in the direction of ether, it will move faster than if I throw it perpendicular. And people did that experiment to see what is the difference, and it turned out there was no difference. So, they realized that there was no ether. It is the only experiment with negative results that actually won a Nobel Prize because it completely changed our understanding of physics. So how you ask question, what you ask question will depend specifically on the subject you're talking about. Often I can't answer in general, except by the example that I gave you. Okay? Yes.
So nature gives us the answers of our questions, right? So for the unified field theory, which part of nature should we ask? Like
universe at its smallest and the largest. So what happened was the universe was born in a Big Bang 13.7 thousand million years ago. And how it was born and how it evolved has the signature of what is the grand unified theory of the universe. And the smallest things in the universe, smaller than nucleus and particle quarks, also has the signature of this basic grand unified theory. So you have to, there are people who look at the large structures of the universe to tell you, to try and figure out the grand unified theory. There are people who look at the subnuclear structure to understand what is the grand. So you will essentially have to be a combination. So there are things, ideas like string theory and stuff like that, which work on the minute scale. And there are people who will look at largest cosmos to talk about inflation and stuff like that. All that will have to come together to give you the grand unified theory.
Thank you, sir.
We'll ask somebody else. Yes, so yes.
Will there ever be a point in time where we know all the workings of nature?
No.
Okay, well,
Never. I'll tell you why. The broad contours of how nature works, we know. So in fact, there's a very famous statement at the end of 18th century. Somebody even declared that physics was over. Okay, they said everything that is to be known in physics is known. Until X-rays came up, until something else came up. There were 2 or 3 phenomena which came up which completely broke our understanding of physics. Okay, X-rays, nuclear physics, and so on. Atomic structure and all that. So nature always has things that she does that we will not understand. She'll always pull up that. At the end of 20th century, we would have said physics is over, except that quantum mechanics is something we just don't understand. We know how it works. We have the mathematical formulation, but we have no instinctive feeling about how it works. It does all kinds of crazy things. So nature probably has more surprises up its sleeves than you and I can imagine. And therefore strange things will keep happening. Yes. That's right.
sir, I had a doubt regarding Like if I want to be a scientist, is it compulsory to get a degree and do PhD in like any form of science, or without a degree, like can we
It
be
depends on what you want to. So, for example, I'm reading a book called Jugaad, which essentially says that you take the whatever is available, currently available technologies, do some Jugaad with it and make a new instrument. Those kind of things can be done instinctively, but they will not allow you to take higher end things. The advantage of getting a degree is that you actually go formally, properly studying everything to is to be done. So becoming a front rank scientist without having proper degree will be difficult. It is best to
Thank you,
pursue science. Yes.
Sir, you said that everything in science is falsifiable, and then again, science is like a tower that is being built on top of previously known things. So, how scary is it as a scientist that something that you may have discovered and something that you used to discover that has becomes falsified, and then so many things on top of that also become.
So yeah, so that fear always remains. But what is happening is that scientists discuss a lot among themselves. They talk a lot among themselves. So all ideas that would not have that were falsifiable get proven to be false very quickly. So it is very rare that a huge amount of structure is made and then the bottom is found bare. There are examples like that. Flat Earth theory is an obvious example where people built up a whole bunch of mathematical models about how planets move and stuff like that. And it turned out that the whole explanation is different if you take sun as the center. So then people have to sit and redo the entire mathematical explanation. But in modern sciences, that is very rare. Yes.
Good morning, sir. I have a doubt like why does nature knows the language of maths? Why not science and different languages?
We don't know. We don't know, but we know that nature likes. Well, actually, you can even ask a question now that you've asked me is whether mathematics is invented or discovered. You can ask whether mathematics is there because humans are there or humans are there because mathematics is there. You can ask the question both ways. And the answer still is we don't know. But we know that if you write something, if the nice thing about nature is that nature is very consistent. If she obeys one rules at one place at one time, she obeys that rules at all the places every time across. Okay. So Newton's laws of motions were discovered in the lab, but they are valid for planets and they are valid for stars and they are valid for galaxies. The nice thing about nature is that once a rule is established, nature has no choice but to obey it all the time everywhere and whatever the size scale you take. And the laws are best expressed in that compact manner. That is how it is. But you can ask questions, the philosophical questions like, are humans here because mathematics is here or is mathematics here because humans are here? And we don't know the answer. Yes. There's a boy there who has a question.
So due to the double slit experiment, we discovered that light has a wave and particle duality.
Correct.
So does the Raman effect occur in both the duality?
Raman effect, okay. See, the thing is, duality is something that is a phrase we use because we are used to visual images. Nature has no such compulsions. Nature light behaves like that. So energy excitation happens because of the electric field in the light photon, in the electromagnetic radiation. So that is electromagnetic part of the story. The collision that happens, you can treat it as a billiard ball accident or everything. So just because you and I think separately of billiard ball and separately of waves, nature does no such thing. Nature nicely merges everything. And nature is not required to explain anything to you. Remember that. Nature works in her own grand way. Any other questions? Yes.
Sir, you in the slide you show us that the sun is yellow and the reflected ray of the sun from moon is white. Why is this so?
I'm not going to answer that. You sit and find it out. The answer I can assure you is fairly complicated and very pretty. Yes. It's the answer will be beautiful. Huh?
As we are saying that AI is taking over the world currently and the field of technology, do you think that one day AI will take over such occupations such as scientists?
No. The reason why I'm saying no but scared to say no, sit down, is because creativity is something we do not understand. Okay. Creativity is something we don't understand. We don't know, as long as we can't figure out how our right brain works, we can never guess how we become creative. Okay, and that create, as long as you don't know how you can become creative, you can never replicate it in AI. What AI does is only what our left brain does. Use language, use complications of language, interpret it, understand the grammar and so on. It's still doing the left brain part of it. The right brain is unknown even to us. So there's no question of programming it. Yes.
So the Florgenson theory is it's abstract. So how is it exactly a theory if it was proved wrong? But how is it like called a theory if the entire solution was based on an abstract substance?
No, I'm not aware of this theory.
Okay.
No, but I mean, abstract substances, for example, this calorific theory for heat has been postulated. People used to think it was a liquid. People worked with experiments. People tried to do a measurement. The measurements did not match. So you threw out the theory. But you can have things working on abstract ideas. There is the basic idea can be abstract.
Sir, just one more question. That how does the Raman effect works in the endoscopy and the X-rays?
Sorry? How does Raman spectroscopy?
Yeah.
What Raman does is that when you put the probe, there's a sensor that emits light. That light falls on the material and that sends you the excited light, not the reflected light, the excited light. That excited light will tell you what kind of molecules exist in your stomach. So if you have, for example, an ulcer, the ulcer's molecules are different. So you can make out that the person has ulcer. Yeah. Correct. Somebody else has a question? Yes.
So wouldn't science be volatile? Because first it was Galileo's laws of physics, then it's Newton's laws of physics, then later maybe 2050 will be someone else.
Yeah. So science, and that is where the fun. Somebody asked me where the science will end. That is where the fun of science is. It is true to the extent of knowledge we have currently. Okay. Newton's laws were considered final word in gravity until Michelson-Morley experiment showed that Newton's laws don't really work. And that is how Einstein's theory. But it is unlikely that they will change. Newton's laws did not nullify, or Einstein's work did not nullify Newton. It simply says that Einstein's world is much bigger. When you narrow it down to our common experience, it reproduces Newton's laws. So Newton's laws were never wrong. And they're still not wrong. And if you are in aerospace, the satellite calculations are all done using Newton's laws. Nobody bothers about gravitational laws there. So we may expand our vision and find that there is a more general rule than the current one. But once you have established that the nature obeys this equation, she will always obey that equation. There may be a bigger theory which may simplify to this for this particular condition. That may happen. But those things will keep happening. Yes.
Wouldn't it be right that for some situations science can be right? Science can be right, and some for other situations it could be wrong, like Galileo's and so on.
Our ideas may be limited by the knowledge we have, but wrong is a very dangerous word to use. I wouldn't use the word wrong. It may be limited in its vision because we don't have enough information.
Okay, thank you, sir.
So I have the doubt if so.
Ah.
So if are there any consequences that can be faced if we force nature to be working upon our wish?
Yes, a greenhouse effect, the runaway carbon temperature problem, everything is that. No, we pushed the nature too hard by air conditioning all the places we live in. The result is that outside is so hot that we sweat like mad. And the monsoon patterns are disturbed. A whole bunch of environmental problems have arisen because we have pushed the nature too hard. Somebody here has a question. That girl here has a question. Just 1 minute. Yes.
So after scientists discover a piece of information, how do they use it? Like what
How
application?
do they use it? Generally, scientists don't bother about using it. It's the engineers who work out that this particular law of physics can be used for in nature. Nobody does everything. Everybody does little bits. And then somebody else puts it together.
Okay.
You had a question. Positron emission tomography is a different thing completely. Positron is not a part of an atom. Okay, positron is not a part of an atom. Electron is a part of the atom. Positrons are artificially created so that they have a certain wavelength by which they reflect in a particular manner, and therefore they can give you subsurface structure, and especially they can give you cancerous molecule, etc. So, in broadly, it is the same, a question of a particle being thrown on a molecule and reflected, but the physics of it becomes more complex. Yeah, you have asked a question. Who has not asked a question? Yes.
So how ethical is it to ask nature questions about humanity and to experiment on those questions on humanity?
Well, I mean, I really want to know why I'm conscious. Okay. So how many experiments will you do is a question of moral ethics of that time. Whether you should sort of, I mean, if I want to be a parent, I'll go to the doctor and say that, look, this is the embryo. Please check everything in the embryo to make sure that I have a perfect child. That is obviously morally dicey. And the beautiful example is that Beethoven, the greatest musician of all time, had 7 brothers and sisters, all died because of genetic problems in their birth. Okay. So by standard medical law, the Beethoven's fetus would also have been aborted. So you don't know which, we really do not understand nature to a level where we can understand everything. So when you don't understand, don't play with it is a standard idea. But yeah, there are questions of morality and authority that you can ask. And we cannot always answer them. Those 2 boys have asked questions. Anybody else is not there, then let them ask. Yes. Photons, light comes out as a radiation. You can either consider it as a wave or you can consider it as a packet of energy. When you consider light as a packet of energy, you call it a photon. Okay. And as a photon, it behaves like a billiard ball. As a light radiation, it behaves in a different manner. But it has dual properties. Yes. Yes. Wait. The boy at the back, yellow t-shirt. Ask.
So, as you told that the work of the scientist is to find things, not use it, and the other people are dependent on scientists to use what they have found. So,
Correct.
are you? Do you mean to tell that other people are dependent on scientists for their work?
Yes. So all major engineering institutions have scientists working with them who understand science, and then the engineering people will convert that into technology. That's a very standard process. Yes.
So how is it?
No, so
Reliable?
no, so there is always a debate. So that is what I'm saying. You may have one idea how nature works. I have another idea of how nature works. I go and ask nature, Baba, do you work like this way or that way? And whichever nature says is the correct way of doing it, we accept that.
But those ideas have already been used, right? And
If they have been used, it means they work. So nature is willing to
but
do
yet
that.
they are challenged, I think.
No, if you have validated your idea with nature, and if nature obeys one rule at one time, she will obey that rule all the time. Nature will not change the equation on which it works.
There's this one in chemistry also about the atoms. Rutherford one, the plum pudding.
Yeah, so Rutherford said that atoms are like plum pudding.
Yeah.
And that scattering experiment showed that it is not like plum pudding.
Yeah.
So that is fine, no? That's exactly how it works. You propose a theory, test it against experiment. Whatever is wrong, you throw away. Whatever is correct, you give.
Sir,
There's one by here. Huh? You need to? That is an impossible question to answer. It is just that if you go to a good institution, chances are that you will get a good teacher. 12 baje nikalna hai. But there are too many questions. Yes. Sorry, if there is a experiments. Ask nature which is the correct theory.
But like,
so one of the things is that anytime you make a theory in science, you have to have predictable variables saying that, look, if my theory is correct, these things should happen. If you don't have sayings that these things should happen, your theory is useless. Nobody will bother. It should have predictability and explanations to why these things should happen, and you check it again, experiment.
so what if all 3 of them have proper practical?
Then it is obvious that there is something common about them, and there is something at a more fundamental level. Yes. I'll take one last question. Just a minute.
Sir, we know that science is like a loop of questions, and you said that science is also multidisciplinary. But how do we know it's also interdisciplinary as well?
Instinctively. If you ask a question and if it requires an expertise from chemists and physicists and everybody, then it's multidisciplinary. It's a question of what the question is. Somebody else here had a question. We'll take this last question and then we'll stop. No, one last question. Yes. Both. The question is research about proving things wrong or right? Both.
Okay.
Proving something wrong also can get you a Nobel Prize.
I'm really amazed to see the questions, quality and quantity both. But I promise you, if this is the enthusiasm, we can have another session sometime as a special one based on only on question answers, no doubt.
As a token of love and appreciation from all of us, I request our director to present a memento to sir.
I I think I don't need to say anything, but yes, a great thank you to Professor Vahia and to all of you, the wonderful, beautiful minds, teachers. I think we have some more programs. Sir has to go to TIFR because he is the president of TIFR Alumni Association as well. So they also have the National Science Day. So he'll be going there. But with a promise, sir, we'll come back maybe with only question answer session. Are you ready for that? Okay, we'll promise. Thank you.
Direct